To motivate our discussion of sampling distributions, let's start off with an example. Say we have a class consisting of only 5 students. We have a good grasp of the population in this case, which we are defining as the 5 students in the classroom. Let's say that random variable y measures the score on an exam for the members of the population. Not everybody makes the exact same score, we assume, so the score is naturally a random variable. After the exam, we know exactly what the distribution of the random variable is. There are 5 members in the population, and there are 5 test scores. Assume that the grades are 70, 78, 80, 95, and 80. We know the distribution of the population, and we know the population parameters. Mean mu is equal to 80.6, and the standard deviation sigma is 8.09. Plus, we know the relative frequency of the test scores in the population. Now let's take a sample of size 3 from the population. Say we randomly chose students 1, 2, and 3 for our sample. They have test scores of 70, 78, and 80. So the mean of that sample, y bar 1, is 76. That's different from the population mean of 80.6. Likewise, we could have just as easily chosen a different random sample, say students 2, 3, and 5. They had scores of 78, 80, and 80. The mean of that sample, y bar 2, is 79.33. Y bar 2 is different from 80.6, and it's also very different from the first sample mean, y bar 1, of 76. Or we could have chosen a random sample that contains students 1, 4, and 5, which would have had a sample mean of y bar 3 equal to 81.67. Again, different from the population mean of 80.6 and different from any of the other 2 sample means. So how many possibilities are there to randomly draw a sample of size 3? Yes? I hope your initial reaction was to say, that's 5, choose 3, obvi. And you'd be right. 5 choose 3 is 10. There are 10 different ways for us to randomly choose a sample of 3 students out of the 5 students in the class. If we calculate the sample mean y bar for each one of those samples, we could potentially have 10 different values. As it turns out in this case, if we enumerate each one of those samples and find its sample mean, we get 7 different sample mean values. Some of them are the same, which makes the particular values more frequent than the others. So this is sounding kind of familiar. We have 7 different possibilities for a sample mean. That is, the sample mean isn't constant. And some of those possibilities are more frequent than others. That is, there's some likelihood that each occurs. That sounds like the sample mean is itself a random variable. In our case, we know the exact population, and we happen to know what its population parameters are, mean mu of 80.6 and standard deviation sigma of 8.09. Those population parameters are fixed. They're constant. They don't change unless the population changes in some way, but let's not mess with that. So the population parameters are fixed, but the sample means are not. They depend entirely on what sample was drawn. If we pick one sample, we get one sample mean. If we pick a different sample, we might get an entirely different sample mean, and each sample mean has some likelihood of occurrence. Therefore, since y bar is a random variable, there's a probability distribution for y bar, and it's called the sampling distribution of y bar. If you drop the class today and you don't watch any more of the other videos, at least take away one thing about sampling. When you collect a sample, don't automatically assume that you know something about the population based on the mean of that sample. We just saw an example of where we could take 10 possible samples from the population, and we found that 7 different sample means were possible, and none of those sample means were the same as the population mean. The sample mean is an estimator of the population mean, but it may not be that great. This is an important takeaway and something we'll address in the next unit. But back to the sampling distribution. One thing we assume with a sampling distribution is that all of the samples taken from the population have the same sample size n. Let's say that the sample distribution has mean mu sub y bar and it has standard deviation sigma sub y bar. As it turns out, the mean of the sampling distribution, mu sub y bar, is equal to mu. That is, the mean of the sample means is just the population mean. That should make some sense. If we average all the sample averages, we should get the population average. And the standard deviation of the sampling distribution is sigma divided by square root of n. That is, as the sample size increases, the variability of the sampling distribution decreases. When the denominator goes up, naturally the ratio decreases. Remember that this is the standard deviation of the distribution of sample averages. The larger the sample size, the sample mean probably won't vary much from sample to sample. The larger the sample size, the less the sample mean would be influenced by outliers. The larger the sample size, the more we're honing in on the sample mean as an estimator for the population mean. If the population of the random variable y is normally distributed with mean mu and standard deviation sigma, then the sampling distribution, the distribution of y bars, is also normally distributed, and it has parameters mean mu and standard deviation sigma over root n. It doesn't matter the sample size, the sampling distribution is normally distributed if the population is normally distributed. But what if the population isn't normally distributed? What do? All is not lost. We have a little thing called the central limit theorem, suggested in 1733 by de Moivre and proved by Laplace in 1810. The word central here refers to fundamental, not center or average, a common misnomer. The central limit theorem is indeed the fundamental theorem of inferential statistics. The central limit theorem, as we define it today, goes something like this. The mean of a random sample has a sampling distribution whose shape can be approximated by a normal distribution, and the larger the sample, the better the approximation. What does that mean? Regardless of the shape of the population distribution, the distribution of sample means follows a normal distribution, the larger the size of n. And you might guess the parameters of the sample distribution, mean mu and standard deviation sigma over root n. So how big does the sample size need to be? Empirical studies suggest that the magic sample size of n is 30, though that's pretty arbitrary. The bigger, the better. The central limit theorem has some useful properties for us, as we'll see a little bit later on. Let's recap, as this is a really important video. We've seen that the mean of a sample collected from a population depends very much on the makeup of that sample. One sample may have a different sample mean from another, and both may be entirely different from the population mean. And that's the same for any sample that we might collect. In the small classroom of 5 students, we knew exactly what the population mean and standard deviation were, but in general, we won't. If we knew what the population parameters were, there'd be no point in sampling. We sample to try to figure out more about the population, so calculating a sample mean has big implications for us. As it turns out, the sample mean follows a distribution itself, and it's called the sampling distribution. It has parameters mean mu, the mean of the originating population, and standard deviation sigma over root n, where sigma is the standard deviation of that originating population. If random variable y describing the population is normally distributed, then the distribution of sample means is also normally distributed. And even if the population isn't normally distributed, the central limit theorem tells us that the distribution of sample means is normal as the sample size gets bigger, more than 30 or so. For example, if the population is skewed in one direction or another, that is, if the population has a really long tail, n will have to be large before the normal distribution works well. The central limit theorem depends highly on the assumption of independence. If the sample isn't random, the statements we try to make about the sample mean could be wrong. Unfortunately, it's somewhat true that you can't just check this in the data after the fact. You have to know about how the data were collected originally. Again, this unit bridges the gap between probability and inferential statistics. Knowing that the sample mean is a random variable helps us in drawing inferences about a population based on a sample. We'll talk more about this in the next unit.